Hello, this is day 4 of chapter 12, sequences in series, and this is about geometric sequence. So the sequence that we looked at was when each term changes by an addition or subtraction amount. So it goes up by 4 or something each time. Geometric sequence is when the rule that the sequence follows is a multiplication rule. And then a common ratio is what that multiplication is. So whatever number that is being used to multiply each term to get to the next term to follow that pattern, then that is what it is. So geometric sequences is sequence which the pattern created uses multiplication. The common ratio R is the number used to find the next term. And it's by multiplying. You multiply it. Okay, so there's a whole bunch of formulas. We've done this before. We had the arithmetic sequences, and this is only for addition or subtraction if your sequence follows that rule. And we could find the series, which is the sum, same definitions. And you have these two formulas that you could use. For a geometric sequence, now this is just a list of numbers, it follows this formula, where you'd have whatever term you're looking for, a sub n, and then your first term times by r raised to the n minus 1. And I just put parentheses around that just to show that the n minus 1 is only connected to the r. And this should make a little bit of sense. The general formula helps us find any term in the sequence. And so any term, if you go down the list of terms or whatever to find like the 10th term or something, you'd have to do repeated addition in arithmetic and repeated multiplication in geometric to find that term, because those are the rules that these particular sequences follow. And repeated addition is the same as multiplication. So we would multiply right here times the common difference, d. And in here, we would do repeated multiplication. And that's why we have an exponent, repeated multiplication of the common ratio r. And then we could also check out the series, but that's coming up later for the sum. Okay, so here's a couple good examples just that are different in how we look at this. So we could see that 8 turns into 20, negative 20 turns into 50. And we could tell right away it's not arithmetic. I mean, we'd have to, we'd be from 8 to negative 20 be subtracting, 28. But then negative 20 to 50, suddenly we're adding. So it's not, we know right now it's not arithmetic. To find the common ratio, so it's not as intuitive. How do you change 8 to get 20? So 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24. And so it's not a whole number. If we know that this is a geometric sequence, we're not multiplying by a whole number. So there is a way to figure out what that ratio is. So 8 times by some number r gets us to be negative 20. Then negative 20 times by some number r is 50. So if you think about that, it's like, 8 times r is negative 20. You could solve this equation and figure out what r is if we know it's a geometric sequence. It has to be the same r for the next one too. Negative 20 times r is 50. That should give us the same r. And then we know what r is, and we could write our formula. Or we could write the next 4 terms. An easier way, or a more streamlined way, is r will always be any term divided by its previous term. That's the same way. That's how we're going to solve this anyway. So I would just say, 20 divided by negative 20 divided by 8, or 50 divided by negative 20. That would give us what r is no matter what. So it doesn't matter which one of these you choose, but you'd get negative 2.5. So if we know that that's r, we found the common ratio. That's how you find it. Take a term and divide it by its previous term. Any term divided by its previous term. And to find the next 4 terms, you're just multiplying whatever you get by negative 2.5. So you could do this if you need a calculator. Just go, open Desmos, and whatever number is the last one on the term, and you want some more, go 50 times negative 2.5. And we get negative 125. And then you could just keep going, times negative 2.5, and it's 312.5. And you keep going, times by negative 2.5, negative 781.25, and same thing again. So that would be the first 4 terms. And it was negative 1953.125. 1953.125. Those are the next 4 terms. We did it. We could do the same thing for b. And notice I strictly said at the beginning, I said it's by multiplying. It's not by adding or subtracting. And in adding or subtracting, I said or subtracting. It's not for geometric multiplying or dividing. We're always thinking of multiplication. So it just makes it easier for us to always have one method. With that being said, if it looks like our number is decreasing in size, and that's not the case for b, part b here, but if it looks like it's decreasing in size, all that means is our common ratio r that we're using to multiply is going to be a fraction that's between 0 and 1 instead of a number greater than 1 to make it bigger. In any event, we want to know some number multiplied to, so 2/9 times some number is 2/3, and that times some number is 2. So again, you could use that little trick, shortcut, where you take a number and divide it by its previous. That's harder in this case because we have fractions. 2 divided by 2/3. That's not as fun, but I'll show you, I guess, a little trick. If you have to divide fractions and you want an easier way, you can multiply their outsides over their insides. So the outsides of a double-decker fraction, I made the 2 to be a 2/1. If you multiply those, we get 6. And I put that on top, and I multiply the insides. And I would get 2. So 6/2 is 3. You could do that on a calculator and get the same answer. 2 divided by 2/3 is 3. But I like this shortcut just because if you remember that it works, or remember how to do it, it always works to divide fractions. So one number divided by its previous, you'll get this. And just for the sake of argument, if I did that with the first 2 numbers, I'd get 2/3 divided by 2/9, one number divided by its previous. Outsides over insides is 18/6, which is 3. So r is 3. So we have the first 3 terms. The next term then would be 2 times 3. So 6 times 3, 18 times 3, 4 times 3, 162. All right. So again, we're doing the same things as asked for. It said find the common ratio. We did it. And give the next 4 terms. The difference between number C, the reason why it's different here, or part C, is our numbers are getting smaller. So you could think, this is fraction multiplication. Another way to find these is that it's multiplied by something to get, 3/4 multiplied something to get 3/10. 3/10 is multiplied by something to get 3/25. So you could think, well, fraction multiplication, the 3 is staying the same on top. So like if I multiply by something, it could be a fraction with a 1 on top. But then we need to know what the denominator is. What is 4? 4 is changing into 10. Okay, so that's not as easy to figure out, but we could always just use the same process of dividing a term by its previous term to find the common ratio if we know it's geometric. So I'd say 3/10 divided by 3/4. And this is, I'll use outsides over insides. This is 12/30. And you could take out a 6 from top and bottom. Divide by 6, you get 2/5. All right. So this is notice if you use 2/5, you're gonna not have 3 on top. And if you want to keep that 3 on top, which maybe we should just so everything looks nicely, all it means is that we need a 1 on top then, so the 3 stays consistent. And if we want that, then we could divide both top and bottom by 2. This will look a little weird. 1/2.5. We're not used to really having a fraction or a decimal that's part of a fraction. But this will work. It will maintain the integrity of having that fraction, the sequence is continuing to have fractions with a 3 on top, if you want it to have this way. Not necessarily needed, but as long as the numbers are equivalent, using whatever fraction you want, it shouldn't matter. So you could continue on. 2.5 is going to be, you're going to start getting some decimals in the denominators. That's why it's kind of like, well, do we really want to maintain the 3 on top or not? 3/25 times 1/2.5. And it's automatically going to give us a decimal here. So we would have to just kind of figure this out on our own. We know the 3 is going to stay on top. We could just do 25 times 5. 62.5. So it would be 3/62.5 for the first one. For the fourth term, because we're starting right here. And we would continue on that using 1/2.5. I'll do one more. I don't really want to waste too much time. This could be completed easily enough. 62.5 is the next term, and this is just the denominators times 2.5. 156.25. All right. So in this one, I opted to keep the pattern going so it looked the same, but that is not necessary. You could get you could get 30/625 right here if you wanted. If we used 2/5 as our common ratio. Okay, and here's the other objective we needed to cover, is that we have this formula, and we want to find the nth term. The nth term is just whatever term we're told to find or we want to find. In this case, it is the 7th term. So what that means is we'll be looking for a sub 7. And we need to know certain things. We need to know the first term. We need to know r, what the common ratio is, and whatever n is. So whatever n is the same as the nth term we're trying to find. So a sub 7, that means n is going to be 7. All right, this means we have the first term. It's easy enough to find. It's the first term, 7. And then times by r, our common ratio. We need to know that. And then raised to the 7 minus 1 power, because we're looking for the 7th term and the 7. To find r, same deal. Take a term divided by the previous. 2.1 divided by 7. That is going to be 0.3. And so we know r, 0.3. And we can put this in a calculator. This is just, we would need to do the exponent first. 7 minus 1 is 6, so you can just put 6. It's 7, parentheses, 0.3, raised to the 6th power. 7 minus 1 power. And we get 0.005103. A sub 7 equals 0.005103. And that answer is perfectly fine. We found the 7th term. Again, there should be, Okay, this one's a little different. Here's what it looks like. This term, we're not given what the first term is. So we're actually going to work backwards to find the first term. And this should use some of the skills that we've learned throughout the year. If we know that the first term is unknown, we know the fifth term. So that's a sub 5 is 24. And we know that r is 2. So we could fill in what we know. If I know that we're talking about the fifth term, then this right here is going to be a sub 5. So and I'll just kind of write it out first. A sub 5 is equal to a sub 1. We're looking for that. We have r, and that is actually 2. I'll write that in. R2. And then to the n minus 1. Well, n is going to be 5 because we know it's the fifth term that we're using. And so the only really thing that we need to substitute in that we know is, well, we know that a sub 5 is 24. So this is really 24 equals a sub 1 times 2 to the 5 minus 1 power. And 5 minus 1 is really 4. So at any point we can do that. So to solve this problem, it's not too bad. We're just getting a sub 1 by itself, and we know a lot of everything else. 2 to the 4th we could evaluate right now. So this would be a sub 1 times 2 to the 4th, which is 16, equals 24. And then a sub 1, just to get that by itself, we divide by 16. So if you divide this, or if you take out an 8, we would get 3/2 or 1.5. And that is our first term. So it's just regular solving an equation, but we have to kind of plug in, using this formula, the things we know. So we have to have a base knowledge of sequences at this point to be able to know what information they're giving us to use the formula. But the formula is not changing. Find the first 3 terms for the geometric sequence if the 4th term is 2.5. And we know that r is 2. So kind of the same situation. The first 3 terms, we would want to start with well, it's kind of 2 ways to do it. We want to start with finding the first term. So I'll do it that way first. We know a sub 4 is 2.5. We know that r is 2. And if a sub 4 is 2.5, we know that n is 4. That's the term we're talking about, we're using. So this would be, if I wrote the formula, a sub n is really 2.5 equals a sub 1, find the first term, times by 2, and then 4 minus 1 power. All right, and 4 minus 1 is going to be 3. 2 to the 3rd is 8, so a sub 1 times 8 equals 2.5. And we'll divide by 8, and without overthinking it, let's just use a calculator. 2.5 divided by 8. 0.3125, or 5/16. Okay, that's just a sub 1 though. We want the first 3 terms. Okay, well if we know that this is 5/16 and r is 2, we would just multiply this term by 2 to get the next term. If we multiply that by 2, 5/16 by 2, we're going to get 5/8. You could use a calculator to prove that, but if we multiply this one by 2 to get the 3rd term, to have the first 3 terms, we'd have 5/4. And if we multiply it again to show that we did have the 4th term at 2.5, it would be 5/2, which is 2.5. Another way of thinking about this, and I just want to quickly cover this, is that we don't know the first 3 terms, but we do know the 4th term. And logically, if we know something about sequences at this point, to get each next term, you just take the term, whatever it is, and multiply it by r to get the next term, and so forth. And we know that r is 2. All right, so if it's this term right here, multiplied by 2 to get 2.5, shouldn't we be able to go backwards and say, well, all right, take 2.5 and divide it by 2? And that would give you this term. Because if you multiply to get some term, you should be able to divide to get the previous term. That's true. So some people will logically know this or intuitively see this, and that's fine. For this type of problem, you could do that. 2.5, and you're going to end up with the same thing, basically. You're going to end up with the same deal. It's just that I had fractions. They would have decimals. Or you could convert them to fractions. All right, I think there's one more example. Okay. Ooh. Write a sequence that has 3 geometric means between 3 and 18, 75, 16, over 16. What that means is we have 3, and then there are 3 terms between. We want to find those 3 terms. So we need to start writing an equation, a formula, plug it in everything we know. This is a sub 1. This is a sub 5. Notice it's the 5th term if you count it up. And we don't know r. We don't know. If we knew r right now, we could just figure out, okay, 3 times r is going to be the 2nd term, and then times by r, we'll get the next each term, and we'd have this sequence. But using the formula, a sub n equals a sub 1 r to the n minus 1 power, we would have a sub 5 be this guy. This is 1875 over 16 equals 3 is a sub 1. We don't know r. But I know that I use the 5th term, so n is 5. All right. Okay, that's 4 right away. R means we have to solve for r. Get r by itself. It has an exponent and it has a 3 out front. So let's divide by 3. We could use outsides over insides, but we get some big numbers. It's basically 1875. So let's figure out what that is as a decimal here. 1875 divided by 16 is this number. And then I could also further this along and just say divide this by 3. And it ends up being 39.0625. And that is r to the 4th power. So we don't have r, we have r to the 4th. What we want is to get rid of this exponent just to see what r is, and then we can use r to fill in these blanks. To figure out what r is, it has an exponent of 4. I need to get rid of the exponent, raise it to the 1/4 power. What this does is this allows us to multiply these exponents because we have power to a power, and 4 times 1/4 is 1. So I chose 1/4 specifically because I know it would multiply with 4 to turn into a 1. So this is r to the 1st now, or just r, and we just have to raise our answer, 39.0625 to the 1/4 power. 1/4. And I get 2.5. So if that's our r, then we should end up with 1875 over 16 if we continue to use 2.5. And I should also keep in mind that I know 2.5 is, if I hit this fraction button, it's 5/2. So 3 times 5/2. Times 5/2 is 15 over 2. Times 5/2 is 75 over 4. Times 5/2, I'm not really sure what that is. 75 over 4 times halves. And I want a fraction, 375 over 8. And we should, if we do one more multiplication, end up with 1875 over 16. The denominators look good because 5/2, I would end up with 16. 375 times 5 is 1875. So we did it. All right, there's kind of a lot in this lesson. So go slow, and this geometric means just make sure you set up a formula, knowing what you know and plugging in what you got. All right, good luck.